So month 1, month 3.
So
yeah, this is the tricky case.
We could start with like 4.
Yeah, let's see what happens when we start with 4.
and we'll definitely have numbers there will definitely be squares here.
Okay. Yeah,
It's just a matter of do they loop.
right. What happens with 4?
So it goes to 7.
No,
Well,
Oh no, it just goes back to 2.
it goes to 2.
well,
Well,
but
but now we already saw that 2.
2 doesn't
never
work.
repeat.
Yeah, no loop.
No loop.
Okay.
so let's try with how about 7?
7.
7 goes to 10.
Okay.
Which
10
goes
goes to 13,
13.
then 16. That goes back to 2.
well, to
Right.
4
To 4,
and then to 2.
Yeah.
So, and that has no loop.
Okay.
So we try to,
10.
well no, that would go back. So we start with 19. Goes to 22. 25. That goes to 5. That
We haven't
goes,
hit 5 before, but
then we go to 8.
oh, we have because
Actually-
5. It was in here,
So
Ah.
2, yeah.
No loop.
so it looks like this case is looping back to
2 mod 2 case.
something
2 mod
in
3.
that 2 mod 2 list
Yeah.
or 2 mod 3 list.
So
Yeah. First, it looks like you're always going to loop down to this 1642, but then starting at 19 shows you can go to 25.
Now we have to start at. You have to start at 28, I guess, or
Sure. 28. What's the square you're going to hit here?
So you're gonna
go along, and eventually you're going to hit what square?
So you're gonna hit 49.
49.
That'll hit a 7, and that'll come back to this.
Go to 7.
Mhm.
We'll go down to 16.
So it seems like every time we do this, we sort of are jumping at the sequence. Sort of comes back.
we don't jump to the same thing each time, but we jump to something that we know will not produce a loop for us.
Yeah. So where do we eventually appear to jump to in all cases?
We jump back to this 2 case where none of the numbers, the 2 mod 3 case.
Yeah,
where
it
none of
seemed-
the
Or
numbers.
somewhere on that list.
Right. It seems like we appear to eventually always jump back to the
2 mod 3 list. That
the
doesn't
2 mod
work.
3 list. So let me show you how the induction proof works here very roughly.
Right?
Okay. So you check, you start, remember how induction works, you start at the beginning, so we check 4. Sorry, I'm trying to write through the tripod here. So we check 4. The next, so 4 does not repeat. So our hypothesis is we never repeat.
Yeah.
Okay, so assume true up to some number, 3n plus 1.
Alright.
Okay, now we got to check for 3n plus 1 plus 3. That's the next number that has a remainder of 1 when you divide by 2.
So here it's 7.
Okay, so here it would be 7, but we're assuming we're true up to some certain point. So what's going to happen here is you're going to loop along. You're just going to keep adding 3, and eventually, we think you end up eventually at mod 2 mod 3. We think somehow you eventually get into that 2 mod 3 loop. Okay.
Alright.
So you keep adding 3, eventually you hit a square.
Yes,
Yep.
that's always true.
Yep. That square has to be congruent to 1 mod 3. So it has to be somewhere backwards on your list.
Yeah.
Yep.
So you go backwards on your list. And so all you have to do is you have to show what we talked about before, that you go lower than 3n plus 1, basically. You go 3n plus 1 or lower. And that's going to be the same idea. You just start crossing off squares on your list, and eventually you're always going to be ahead. So you go backwards, and you end up in here to something you've already checked before. and you've assumed that that doesn't repeat.
So,
So it's basically the same idea. You go back down your list when you hit that square. So that's the only tricky thing, is you have to show that the square root sends you backwards down the list. And it's not too hard. It's basically the exact same argument I showed you before. You're crossing off numbers. You're going to hit it. There's going to be whatever the first open number is going to be the first square you hit. And
it will not repeat.
right, it's less than where you started.
Yeah.
So that means it won't repeat.
All right.
So not too hard.
So,
I mean, for an International Mathematics Olympiad problem, that is not a hard problem. In fact, it can be explained to kids.
Yeah.
But want to hear something interesting about this year's Mathematics Olympiad?
What?
It had probably the hardest problem ever.
Oh.
So maybe we might talk about that tomorrow.
All right.
All right.
And I expect you to solve it. Ah! All right, high five, guys.